Bismillahirrahmanirrahim. Topic of my project is hydrogen atom using MATLAB and Mathematica. Main highlights of this project are hydrogen atom in parabolic coordinates, hydrogen molecular orbital energy in case of hydrogen atom, the angular equation for hydrogen atom, the polar angle equation of hydrogen atom, calculation of the spherical harmonics, just the mathematical analysis of radial function and hydrogenic wave function visualization, the energy level for the hydrogen atom. So first we will consider hydrogen atom in parabolic coordinates. Hydrogen atom in parabolic coordinate is useful because it helps in solving Schrödinger equation for hydrogen atom, and it is basically the major recognition to higher eigenstate, and it is connected to the existence of the hidden symmetry and is useful for solving the Coulombic problems in electromagnetism. In this case, n is equal to n1 plus n2 plus mod of m plus 1. It is principal quantum number, and the mathematical commands are shown over here, and we have attained the output as this one. The output is showing that we have got a contour plot for the real part of wave functions in xz plane, and in this output we got this black dot, and this black dot is showing nucleus. The red arrow is useful for showing the presence of the electric field. Then there comes energy in case of hydrogen atom. For calculation of energy in case of hydrogen atom, first we need to consider the Hamiltonian in hydrogen atom, and the calculation of energy of hydrogen atom, it depends upon solving the time independent Schrödinger equation for electrons in the hydrogen atom. MATLAB code for the this case is shown over here. In this case, we have used the command line space. Line space basically return the n linearly spaced point, and the mesh grid is useful for the production of three-dimensional coordinate array, and cron is used for returning the chronicle tensor product of matrix A and matrix B, and eigs, these are basically used for returning the eigen values based upon the sigma function. If we want 3D plot, then we need to manipulate another command, that is the scatter command, and we will get the MATLAB output as shown over here for 3D plot. Let us consider the simple example of an electron, and it is moving from n is equal to 3 to orbit with n is equal to 2. Mean when hydrogen atom gain 3 electrons, we need to determine energy of photon in joules. Energy release in Bohr model is given by this equation. In this equation, Z is equal to atomic number, NF is the final orbit number, and I is the initial orbit number. When Z is equal to 1, as we are considering the case of hydrogen atom, so we will use atomic number which is equal to 1, NF is equal to 2, and Ni is equal to 3. The MATLAB code is shown over here, and we have achieved the output, that is minus 0.11 joule. It is the energy of the photon. Then is the angular equation for the hydrogen atom. This equation is solved by using the Laplacian in spherical coordinates. The Schrödinger equation attains this form, and the spherical harmonics, they are also plotted on the MATLAB. First we need to create a grid, then after that we will calculate the harmonics, and then after applying the spherical coordinate we will get this MATLAB output. and this is the plot for the spherical harmonic function of the hydrogen atom. Now the angular equation for the hydrogen atom, for the angular equation of the hydrogen atom, we need to rearrange the Schrödinger equation and multiply that equation by the sine squared theta, and after rearranging that equation we came to know this thing that the first two terms depend only on theta and the last term is dependent upon phi, and we have attained the non-trivial solution as well. And the non-trivial solution is that the sum is zero if the groups of the terms each dependent on the single variable is equal to same constant, let's suppose m squared. The polar equation of hydrogen atom is achieved by using the equation B, and after rearranging and evaluating the first term of equation B, we have got the equation C result, and using change of variable x is equal to cos theta, we will attain our desired result. The MATLAB animation for cos theta is shown over here, and in this case we have just used the marker plot, line plots, and also the graph properties. Mean axis is 0 and then is the 6 pi minus 1, and also the grid is on. Then is the polar angle equation for the hydrogen atom. After solving equation C, we will get the polar angle equation of the hydrogen atom in this form, and putting derivative in equation C and dividing whole equation by sine squared theta, we will get the equation of the associated Legendre polynomial, and when m is equal to 0, we will get the function having the single argument, and when m is equal to 0, the associated Legendre polynomial can be generated from the Legendre polynomial, and using change of variables, that is x is equal to cos theta, we can generate the function for the spherical harmonics, and over here the PLM cos theta, it is the associated Legendre polynomial. The calculation of the spherical harmonics is simple. First we need to establish the grid of all values, and this grid will be the combination of all the values including the azimuthal angle as well. Then the MATLAB command for this case are shown over here. When L is equal to 3, then in that case our required MATLAB command are this one, and for spherical harmonics we have got these MATLAB commands, and after converting all the spherical harmonics into Cartesian coordinates, we will get this output. And now let us consider the mathematical analysis for the radial wave function for hydrogen atom. In this case A and L is the normalization constant, but the question here arises is that how does one determine the expression of the radial wave function? So for the determination of radial wave function, we need to consider some special function, and let us suppose that function to be the associated Legendre polynomial, which is the solution to the Schrödinger equation. Now the associated Legendre polynomial is defined in terms of the Legendre polynomial, and after using the change of variable technique, we will attain the differential as the asymptotic behavior of the radial wave function of the hydrogen atom, and using the normalization condition of the associated Legendre polynomial function, we will attain the wave function of the hydrogen atom. And the equation 8, it is the general form of the radial wave function of the hydrogen atom. When we will put n is equal to 1 and L is equal to 0, the radial wave function for hydrogen atom will achieve this form, and when we will plot that on the MATLAB, then in that case we will get this result. In this MATLAB code, what I have done is that first I have solved the Legendre polynomial part, and then I have solved the associated Legendre polynomial part. Similarly, when we put n n is equal to 2, L is equal to 0, we will get the radial wave function for that is the R20 for the case of the hydrogen atom. Same is the case when n is equal to 2 and L is equal to 1. And first of all we will solve the first part of the Legweri polynomial, and then we will solve the part of the associated Legweri polynomial. As you can see, by changing the value of n and L, we can get the different result for the radial wave function of the hydrogen atom. Now let us consider another example. Suppose that we are provided with this function, and in this function a is equal to 2 pi, and it is the Legweri polynomial of first kind, and we need to plot f of r using MATLAB. It is simple command. Over here I have used the mesh command. It is useful for the production of the x, y, z three-dimensional figure, and we have attained this result for the f of r function, which is provided in the above example. Let us consider another example. In this example we need to find the sigma for the wave function of hydrogen atom, and we have assumed that this wave function is in the minimum state. Suppose that the required wave function is this one. For this case, what we have to do is we have to suppose that the charge on the nucleus of hydrogen atom is 1, and over here a naught is there. A naught is basically the Bohr radius, and after applying the whole wave function and using MATLAB, we will get the value that the minimum value occur at this minimum value is occurring in this way. So we will get our output as this one. And now let us consider the relativistic energy level for hydrogen atom. In non-relativistic quantum mechanics, the energy level of hydrogen atom, they are given by the Bohr's formula and the Schrödinger equation, and in Dirac relativistic theory this degeneracy is partially resolved and energy is found to be dependent upon the angular momentum quantum number as well. So the relativistic as well as the radioactive correction to the hydrogen energy level, it can be written as shown in this figure. And over here in this demonstration, it is basically the conceptual verification for the fine structure constant from the 0 to the specific value or the its actual value. So after understanding this, we will attain these MATLAB Mathematica commands over here, and the Mathematica results are mentioned in this over here. When n is equal to 1, the graph would be this one, and when we will turn on the schematic energy level diagram, the schematic energy level diagram for non-relativistic level, then is the Dirac equation, and the hyperfine structure for the hydrogen atom is shown over here when n is equal to 1. Similarly, when n is equal to 2, these are our graph, and the schematic energy level diagram is this one, and when n is equal to 3, the schematic energy level diagram is this one. The n is equal to 1 is non-relativistic part is shown, then is the Dirac equation part, then is the lambda shift, and the last one is the hyperfine structure. Atom molecular orbital. The orbital in case of hydrogen atom is defined by the quantum number. These are the MATLAB commands for the basic molecular orbitals of the quantum number, and in this case the radial nodes are there. These radial nodes are determined by the Legendre polynomials, and angular nodes are there which are determined by the Legendre polynomial. And the small function make color is used, which is used to give some preloaded color values, and it is also useful for coloring the skin of the orbital functions, and plot solid iso surface is used, and plot cross-sectional areas, and the plot wave function, sine isosurface. They are good start to visualizing the data for the plotting of the molecular orbitals. Then is the plot cross-section isosurface. It has the color bar, and these are multiple of the cutoff values which are labeled in the constant cutoff. And after manipulating these commands, we have attained this MATLAB result, and we can also rotate these orbitals. And for example, this one is the 1s0 orbital cross section, and I am rotating in all the directions. Similarly, we can also rotate this cross sectional, that is the 2s0 orbital cross section, then is the 3s0 orbital cross section, and then is the 4s0 orbital cross section. And similarly, we can also get these type of the molecular orbital for the case of the 2p plot. And after plotting or manipulating these MATLAB command, we will get our required result as 2p naught is equiorbital cross section as this one. And we can also plot 3D plot for the hydrogen molecular orbital 3D. And after calculating and plotting the wave function and isosurfaces, after setting the dimensions of the plot, we get this MATLAB output. And the MATLAB command for 3p plot, these are also the same as the previous one, and only changes that here we have considered the 3p orbital, and these are its MATLAB outputs. Similarly, for 4f plot, we have attained these MATLAB output. And for the case of the hybrid orbital, let us plot SP plot. We first need to define the constant as well as the orbital shape, and we can rotate all these orbitals and plots as well after setting the command of the rotate command. And this one is the MATLAB output for SP1 orbital and SP2 orbital. Similarly, we can also obtain the hybrid orbital MATLAB command, that is for the SP2 plot. First we need to define that constant and original shape, and after doing the generating xy space, and then is converting to the spherical radius and plotting that figure and setting the dimensions of the plot, we have attained this MATLAB output for the SP3 plot. Then is for the SP3 plot, and these are its MATLAB outputs, and SP3 or 1 orbital is considered over here, and SP32 orbital, SP33 orbital, and SP4 orbital is considered. These all are the hybrid orbitals. Then is the MATLAB command for SP 3D plot. Over here we need to define first constant and orbital shape, and after defining we will generate xy space. After converting it to the spherical radius, we will plot our wave functions and set the plot as set the dimensions of the plot, and we will attain this MATLAB output for the SP3D orbital, which is the hybrid orbital for the case of hydrogen atom, and we can rotate these orbitals as well. And now the MATLAB command for hybrid orbital SP3D2 plot are shown over here, and we will get the MATLAB output as this one. It is for SP3D1 orbital, SP3D2 orbital, SP D3 orbital, SP3D4 d4 orbital, sp3 d5 orbital. Then is the generating function, wave function, for when we have to consider the hydrogen atom wave function visualization and its conversion from one orbital state to another orbital state. First we need to generate our wave function. Here in this case we will calculate the hydrogenic wave function as well, that is the hydrogen atom wave function visualization along with its conversion from the one orbital to another orbital. First of all, what we need to do is we need to generate our wave function, and then we will resize and manipulate that wave function. And as far as the physical calculation on that wave function is concerned, first we need to calculate the dipole moment along with the calculation of the transitional state. And as far as the plotting of wave function is concerned, we need to plot the psi wave function as well as the below sphere wave function, and then we will animate the transmission. Then is the, as far as the miscellaneous command is concerned, first we need to get the psi form NLM, and also then after that we will get the psi list, and we need to prove this thing, that is it electric dipole transition or not. And then we will look for the L nomenclature along with the parastate L label with the Z crossing. Let us consider the JUI operation overview. In opening function we set up the various constant parameter and the default parameters, and after that we need to animate our operation. And the purpose of this animation operation is that it helps to load initial final wave function from the wave function list. And then one of most important thing is that by holding off the rescale until the user start animation, it helps to increase the responsiveness of JUI list. And then is the state selection. It is basically the core function of the state selector list or the populator, and these are basically I update list and also the I update M list and I update L list, and these functions help to populate the list box with the allowed L, or you can say the M values, which are corresponding to N or L. Let us consider the MATLAB commands of this one, and this one is the transition visualization of JUI function. Let's start this over here. In this case my initial state is N is equal to 4, L is D, and M is -1, and we are moving toward the final state, that is N is equal to 1 and L is equal to S and M is 0. So in this way we will attain our final state as this one. As you can see over here the inner surface is shown with the blue, which help to represent the nucleus. As you can see, now we have attained our final form, N is equal to 1. Now let's suppose I want to move from state 3, and I set the value, that is the -2, and final state would be 2, and L would be P. Now let's start. Here we are moving from initial state N is equal to 3, and we will get our form of the 2P in this case, that is our final form, and the M is supposed to be equal to 0. Remember this thing, that this is not at all valid for the electric dipole transition. Over here we have considered the below sphere representation, and also I can rotate this thing in any direction as well, overview, mean dorsal or ventral view. And now let's suppose I want to move from initial state, that is 4, and L is equal to F, and my final state is this one. So let's start. What will happen to our initial and final state. Initially it was having this state, and now you can see how it is changing from the initial form to its final form, that is n is equal to 3 orbital, and over here L is equal to p and m is equal to 0. In this way it will attain its form. And now this one is the final state. Over here n is equal to 3 and L is equal to p. Now let us move towards the 3S state, and our final state is n is equal to 4f. Okay, now let's see what will happen if we set these conditions. Mean the initially it was the orbital, that is n is equal to 3, L is equal to s, m is equal to 0, and it is moving toward n is equal to 4, L is equal to f, and m is equal to 0. See how it's changing. Now this one, here we have attained our final form. Similarly, we can switch from any state which we want. Now for example, I want to move from initially 1 to this 4f state, and I set that m is equal to 0. Now what will happen if I want to do this? Slowly and gradually it is changing its shape, and n is equal to 1, L is equal to s, m is equal to 0, and n is equal to 4. That is the final state, and over here m would be equal to 0. See how this is changing. In this